Welcome back to Organic Chemistry. Today we're going to talk about rearrangement. That's our topic. What I mean is molecules moving around, or parts of them in fact, swapping places. So if we imagine this molecule and we're going to make it react, so first of all we want to turn it into a carbocation, we want to make it more reactive, so we need to make our OH into a leaving group by protonating it. There we go, that makes it a good leaving group. And so we can lose that water. It's going to take its electrons with it, like that. Double arrow is 2 electrons, remember? And then we're going to end up with, I've lost my eraser, we're going to end up with this species here with a positive charge on here, and this is a going to rehybridize and be a flat triangular group, carbon, with this positive charge in the vertical plane. So let's put the hydrogen on, which would be there. Now we've got a carbocation, but it's on this secondary carbon, and as we know from before, a carbocation or a radical, but a carbocation is particularly more stable if it's at a higher substituted place than it is at a lower substituted place. So on the end it would be worse. Here it's okay, it's a secondary one, and here it would be better at the tertiary position. So with 3 carbons on it and 6 and 1, so 7 hydrogens helping it out with their bonds, with the electrons out of their bonds. So what we can do here is we can imagine that there's a hydrogen on here, and it can attack. So it can go across to here. If the hydrogen shifts, this is called a hydrogen shift or a proton shift, because the hydrogen is moving across to here. So let's resolve that arrow. If that happens, we end up with H2 here. We've got a normal part of the molecule and the plus has moved. So if we were doing an SN1 type substitution, our substitution would happen on this carbon instead of on the one that we were intending it to, or instead of the one that we were expecting it to. If we do this in reality, we will get a mixture of products. This would be the minor product. There would be less of this because the carbocation on this position is much more stable. However, if we give it some really reactive thing to cover this, so a good nucleophile that can attack this positive position, then we will get more of the original position because it reacts faster. If we give it something that's not very good at attacking, then it will tend to be able to rearrange first, and it will make this. Also, temperature will play a role. As you can imagine, this is usually a pain because it causes reactions to go not as we intended, and we tend to get a mixture of products. But it can also be used to move a functional group to somewhere where we would like it. So if we know that we want our functional group on here, then we can do a reaction that is likely to result in a rearrangement, and it will tend to move to here. Now let's imagine that we want to add water, HOH, across this double bond. So adding water across a double bond is the opposite of an elimination. We're doing an addition reaction across a double bond. We're going to add HOH to it. If we do that, we will have relatively simple rules normally that go on, but we will have a possibility of rearrangement happening. So let us see what happens. So we're going to add H plus and OH minus, because very often these reactions take place in 2 steps. They don't always, but then they're usually more than 2 steps. So what we want to do is add the OH to one end of the double bond and the H to the other end. Now the problem that we have here, compared to the previous example, is that a double bond has an excess of electrons rather than a deficit of electrons. So it's not very easy to attack it with a negative species, with a nucleophile. Therefore, the H plus is going to do the first step for us. We can add the H plus to either end. And if we add an H plus, let's put the H plus in the middle. So we can add the H plus to there, and that will either take both electrons in this direction, which would make, let me draw it like this, it would make this intermediate, or it can go on the other end, logically. But obviously this positive ion on the end is super unhappy. We already established that that's not going to be a preferred result, putting a positive charge on the end of a molecule when it could have gone in the middle. So we are more likely to put our positive charge in the middle. That's going to be the more common product. And then we've got back to the stage that we were at before, that our hydrogen here could do the same thing that it did before and jump across, moving the carbocation, the positive charge, onto here. Sorry about the squeaking. So that's put our hydrogen back over here, and we've now got a plus here, which will react with the OH minus. So now when we take those three possibilities, let me draw the three possibilities, I'll come back to you. So here is our start of our reaction. First of all, we add the H plus to our double bond. So that makes a carbocation on one of these two carbons. If it's the end one, it's stuck there, and it could move, which would allow it to become this one, and then it could move again. If we have it on the second one, the second carbon along, it's unlikely to move in this direction because that would make it less likely or less stable, and so it's more likely to move in this direction. So it would be a hydrogen shifting to here, here would be a hydrogen shifting to here. It could do that after the beginning. Then those three intermediates can now react with the OH minus and produce their products, which would be OH, and this one could form the secondary product, and this one could form the primary product. Like that. Not very good at drawing molecules anymore, I've got out of practice. So we've now got a kind of world of possibilities. This is an example which really does form all three, and this is actually the most common product because this is the most stable carbocation that it can form, because obviously if it goes to try to go anywhere else, it gets worse. It isn't only hydrogens that can move, however, although they are preferred because they're kind of small. But if we have a molecule like this, where if we protonate this, making it positive, and then remove it as water, so we get a carbocation on this position here, we will end up with a similar case. If we have a hydrogen here and we move it, we would make a primary carbocation, and those are super rare. That's very unlikely to happen, so we're not going to do that. It's already on a secondary position, so it would like to get on a tertiary position, but there are no hydrogens that it can steal in this direction to make itself better, and therefore it's going to grab a methyl group instead. Let's have this one. So if it takes the methyl group with its electrons, that would be this coming over here. Let's move it over here like that, and that would make this carbon positive instead. Obviously with this case, because we're moving a methyl group, it makes where the positive charge is going have one less carbon on it, and so very often it doesn't happen because it would make the carbocation less stable. But if we have a very branched structure, or if we have a very branched structure, then we can do that, or a ring or something. So then we've got our positive charge here, and we can do the rest of the reaction. We could do an elimination this time, and this will eliminate in one way or the other. So it could eliminate to go to form this product, but that's not going to be as likely as eliminating the hydrogen that is still here and forming this double bond. So if we lose H plus into the solvent, we end up with this double bond here. That is the opposite of the reaction that we just had, obviously, and we end up with a more spread out branch structure because of it. This is obviously more stable because the double bond is fed by all of these methyl groups. Introducing a couple of things at the same time. The examples that you might see on the internet often include a lot of rings, because this is a good way of making rings, and it is also a problem when we have rings involved, because they tend to react with themselves. That's because they're already in the right orientation. So if we look at this molecule, it's got lots of double bonds in it, so it's mostly flat, which means that this hydrogen here and this hydrogen here are pointed exactly to the right position where we would imagine that a carbon should be if it was graphite. So our geometry is already pretty good for connecting across here. If we take this bromine off as a radical, which we can do with a metal, because we want to take it off with one electron and make radical a single electron uncharged rather than the carbocation that we had before. That's obviously going to end up on here. Then we can do a hydride shift, which is exactly the same, or hydrogen shift, let's do it like that, which is exactly the same as we had before. Sorry, dot plus, I'm an idiot. I just told you it was a radical, and then I draw a positive charge. It's a dot. Then our hydrogen has to come across with a single arrow, single armed arrow, because it's only moving one electron and the other one stays here. That we can resolve again, squeakity squeak, making a radical on this position. This radical is now able to attack across. The mechanism is one that you will come across in polymer chemistry. So if a radical here attacks a double bond, it generates, the radical moves, it generates a new bond. Let's do that. So this double bond goes, it generates a new bond across here, and it moves the radical to this position, because obviously we can't destroy the radical, and now we need to, or we want to get rid of this hydrogen on this position, which I wanted to attack directly, but that's not what happens. The radical interacts with the double bond, and then the second step occurs. Obviously we've done a really bad crime. We've broken the ring. It now can't do its ring stuff. Benzene rings are particularly stable, and now it is no longer a benzene ring because we took one of its bonds away. So now that can reform by taking this electron and this hydrogen, leaving us with the product. What we've really done is we've shifted a hydrogen around the molecule, which is what I actually wanted to say, what I actually wanted to show you. This is quite a common accidental reaction. Sometimes it's deliberate. It also happens reasonably often in biology, which is why you need to know it. Obviously for us, we're not going to concentrate on these horribly ugly multiple ring molecules, but I wanted to show you one because I know that these are very often used as examples, and that's because when you flatten a ring out, or when you flatten a molecule out and it's got rings in it, it brings groups very close to each other, and then they react more often. So we can make this reaction happen. If we do it at low concentration, the probability of this bond forming inside the molecule is quite high, because otherwise it would have to find another molecule of something. So to summarize this topic, carbocations rearrange, and they rearrange typically to lower their energy, or they rearrange typically to a lower energy form, and that would be by moving a hydrogen most often that moves the positive charge to another carbon, or another atom is better said, because it could be a positive charge on a different atom, but they're typically on carbon. If we do that, we can move it to a more substituted position, or a position where there are electrons being donated in, so we have an electron donating group attached to it. Or it could be moving away from an electron withdrawing group. So if we had a trifluoro group on, for example, which pulls electrons away, our cation wouldn't attempt, because it doesn't have soul, but it would move away from the electron donating, electron withdrawing group, it would move away from the electron withdrawing group, because obviously that is less stable, and it can get to a more stable position if it moves away. It will also move to a more substituted position with methyl groups, so that it can be stabilized by the hydrogens in there. Radicals are similar. They will tend to move hydrogens first as well, because they're smaller, they're easier to move, and they can also move methyl groups too, or longer carbon groups, and we will see them do that in a later course, because that is one of the things that happens during degradation. The mechanism that I just showed you is a preliminary for the next topic, which will be carbonyl groups, where we've got a C double bond O, and we're going to interact with it in interesting ways.